Hey guys, welcome back to another episode of Simuleos. Today is going to be an absolutely fantastic day because it's the first day I'm back after a week of being sick. So I'll be honest, I'm not completely better. I still have a whole bunch of pressure behind my right eye, which makes me feel a little bit weird, but that's okay. Hey, with Takanai, truth is, let's see, a week ago, last Wednesday, I think it was the last stream I'd done for a very long time, and, well, okay, not a very long time, just a week, right? That's not that long. But, yeah, so it started with a throat itch. Then after that, I started getting problems with, congestion and stuff like that. Got a headache. I don't know. Just this weekend was really bad. But, as of now, it's officially better. Not as good as it could be, but better. So I think I can handle a full stream. We'll see how far we go. Anyway, hey guys. Hey, Gustorn. So what should we do? Well, let's go ahead and get started like we always do by opening up Zernal and talking about the problem. What just happened there? Oh, I am already screwing up. Zernal. Okay, so what are we talking about? Well, what I want to do is work on dynamic Huffman encoding. My idea was that we could finish this up, well, by about now, but of course, because I was sick for about a week, that didn't exactly happen. But hey, I don't think we're that far off. I think we can finish it probably by the end of this week, start of next week, sometime like that. That's my goal. So we'll see how far we get. Okay, so let's start with the basics, which would be Huffman encoding. Basic Huffman encoding, not dynamic Huffman encoding. So let's just go through it one step at a time. So here's the idea with traditional Huffman encoding. The idea is that you have encoding. There we go. The idea is that you have a bunch of letters coming into you or coming into your preview area with a particular frequency. So let's say A has a frequency of 60% of showing up. B has a frequency of, let's say, 10%. C has a frequency of 10%. 1 second. D has a frequency of 10%. And E has a frequency of 10%. That should add to 100% total. Now, what we do is we put them down into a list like this. Now, there's many ways in which we can create this tree. It doesn't have to be like this, but personally, when I'm drawing it on the board, I find it a lot easier to kind of draw them from left to right because it just, I don't know, it makes more sense to put them into a list, a descending list like this. Okay, so we have all of our different leaves here, external nodes, and then we add them together lowest first. So here are the two lowest. That's going to add together to 20. Have you seen the Acapella Science song about William Hamilton on YouTube? No, I have not. With people like Derek Mueller and Hank Green, inspired by Alexander Hamilton musical. I have not at all. But I mean, I don't know. I think it's probably pretty good. Okay, then we add together the two lowest again, which will make 20%. Add together the two lowest again to make 20%. 40%. I'm bad at math. And then add together the two lowest again to make 100%. Then we go back through and we put ones and zeros on all of the branches. And then we just basically create our new alphabet from there. So we say A is going to be back here, 1. B is going to be 0, 1, 1. C is going to be 0, 1, 0. D is going to be 0, 0, 1. And E is going to be 0, 0, 0. So I never actually saw the Hamilton musical. Does that spoil it at all? Okay, so here is our new set of code words, right? And here you might think this is kind of weird, right? We just did Huffman encoding, and yet after doing our encoding scheme, we see that A has a has 1 bit, right? It only has 1 character. Meanwhile, B, C, D, and E all have 3 characters. And this might seem a little bit weird to you, but it makes a good bit of sense because A has significantly more frequency, has a much higher chance of coming in. And the idea behind Huffman encoding is that we're minimizing the total number of bits in the end, right? And so the idea then is that, well, If A comes in with much higher frequency, then in that case, A should have fewer bits. And because in this case it has way more of a chance of appearing than any other characters on this list, it really does make a good bit of sense to have it have only one character. Meanwhile, all the other four, having the same frequency, same low frequency of appearing, should have, you know, the same number of characters roughly. So that kind of makes sense if you think about it. Hopefully that's a decent enough description. Now there's a way to quantify this with Shannon entropy and stuff like that, but we're not going to go into that. We could, but that's okay. No, basically the same song as the first song in the musical, just with lyrics about Hamilton, Hank Green is Schrodinger. Ah, that's neat. Okay, so what are we going to do next? Now let's start talking about the what we're going to do today. Hey Krabs, it has been forever. How are you? Except for terrible annoying internet connection, which seems Twitch is getting worse and worse. Yeah, so what have you missed? Well, we've done a couple more visualizations here and there. We've done, let's see, I don't know, quite a few things, but man, I'm so glad you're back. That's awesome. I'm actually a little bit sick today. Sorry about that. But yeah, right now we're working on dynamic Huffman encoding. We are doing some visualizations of it, trying to understand how it works. So it's going to be a bit of it's going to be a slow day. I'm not going to lie. I'm a little bit sick. We're working on new stuff, so that's okay. But hey, I'm so glad you're back. Let's see. Spoiler, Hank Green Schrodinger. Yeah, so I don't know. I'll look into the musical probably over breakfast this morning. I end up watching a video during that time. Let me think. I can't really specifically point out things outside of that you've missed. Just for this particular project, we just finished visualizing basic Huffman. Now we're working on dynamic Huffman, which I'm going to describe right now. So the algorithm that we're using for dynamic Huffman encoding. Huffman, 1 second. Encoding. Forgive the fact that I did camel case here and then I didn't there. Anyway, dynamic Huffman encoding is going to be the Vitter algorithm. As always, let me very quickly look up a paper so you guys can more easily follow what we're doing. So here, let's go here and let's see. Algorithm 637, 673, 637, 673. There we go. And let me grab this. Grab this for you guys. Here is one paper, which is the one that I will be following mostly. And then we have another paper which gives some pseudocode to look at, which will be design and analysis. Oh shoot, I did this backwards. This paper is the one with the pseudocode. The one that design and analysis of dynamic Huffman codes. Clearly I'm good at spelling. And here we go here. In this one, oh no, actually wait a minute. I think this is the one I needed a special link for. 1 second. Should be here. There we go. This is the one I need. Okay, once I give you guys this, you now have access to the two papers that I'll be working off of. And I'll kind of show you guys the pages we need to go through to find necessary material. That's fine. Okay, so dynamic Huffman encoding. The algorithm we're using is the Vitter algorithm. Here's the idea. There are 4 things we need to keep into account. The first is something known as implicit numbering. Okay. So I'm going to take this a little bit slower, but not as slowly as we did the first day. Here's the idea. If we have a tree, just a simple binary tree, again, kind of like the Huffman trees, in fact, exactly like the Huffman trees, we're going to number all of the internal and external nodes. Just so that I'm clear, I'm going to put all the external nodes as squares and all the internal nodes as circles. Now, the implicit numbering scheme is set such that we increase in number going this way, and again increase in number going this way. So the numbering scheme looks like this. 0, 1, 2, 3, 4, 5, 6, where 6 is the highest. Where did the demons go? You're talking about the Maxwell demon code? That actually we made a YouTube video on. It's up on my YouTube channel, which is right, 1 second, exclamation mark, UYT. if you want, you can take a look at that. I think you mean that demon. We've done a lot with actually the visualization code from there. In fact, we did another video on eigenvectors, which you can also look at using very similar visualization scripts as to what you helped us write that day. It actually turned out very, very well. I'm happy with that. It's highly optimized vertically. It's not really meant to be educational. That's fine. I think it's fine. We'll see. I couldn't actually find. I spent hours, more than hours. I spent a very long time looking for a description of the Vitter algorithm, and I just couldn't. I couldn't. No matter how hard I looked for this, I could not find a better description of the Vitter algorithm for dynamic Huffman encoding. I don't know why, I just couldn't. And so the only one that made sense to me was this article written by Jeffrey Vitter. Now, we aren't going to be doing the exact same thing, but the algorithm itself, I think we have a pretty good grasp on now. If you have a better link, let me know. Just remember this, let me see. Open link, let's see what we got here. Adaptive Huffman, tree manipulation. Yeah, I saw this, but the problem was it didn't actually go through the Vitter algorithm, right? It went through, let me see. So the Vitter method is a product, it went through down here, right? So it explained the dynamic Huffman stuff, right? With this kind of diagram, which is the exact diagram that we'll be using, right? But it kind of like mixed FGK and Vitter in the end. Still reading Think Bayes, and it's so good. Still continue to study machine learning. On the subject of trees, I just remembered this. Let's see what we got here. I'm a developer of the family tree software. Okay. I have no problems until one of my customers mailed me a bug report. The problem is that he has 2 children with his own daughter, and as a result, he can't use my software because of errors. Those errors are a result of my various assertions and invariants about the family graph being processed. For example, after walking cycle, the program states that X can't be both father and grandfather. Why? How can I resolve those errors without removing all data assertions? Okay. This page is Vitter only. It only mentions FGK. Okay, let me see. Is this the tree is initialized prior to any reading has been done from the file. My tree and my NYT are the same. And the sample file we will read consists of a string AARDV as reproduced following the example from data compression by Khaled Sayud. Sorry about that. Okay, I'll take a look at these. Unfortunately for today, I'm probably not going to be able to look at it like during stream. This is probably something I need to take a look at afterwards. But I'll basically take a look at it during work, print out what I need to print out, and hopefully have some time tonight. Today is Wednesday. Yeah, I should have time tonight and go from there. Yeah, I figured it was, yeah. Okay. Well, we'll take a look at this if we get stuck, and we'll go from there. Okay, so first let's describe this Vitter algorithm. So here's the idea. We have implicit numbering. The implicit numbering, again, is just this numbering scheme that allows us to keep track of all of the external nodes, being the leaves with all of the character values in them, and the internal nodes being 4, 5, and 6, these guys up here. Okay, you might think that this isn't particularly useful, but there are reasons why we need it. Okay, so next, the next thing we need to talk about is after implicit numbering, it is, 1 second, what am I thinking about here? There are 4 things we need to keep into account. It's been a week. I don't remember what all 4 of these things are, but I can tell you this. We have, a method known as slide and increment. Okay, so now let me see, because I'm pretty sure I am mixing something up here. Let's see, what do we have here? Design analysis of dynamic Huffman codes. We'll move on to a particular page here. Oh, okay, I know one. And I know where to find these 4 bits of information too. They're actually on the Wikipedia article for dynamic Huffman encoding. So dynamic Huffman encoding. Here we are. It's right here. Implicit numbering is the invariant, and the invariant There we go. The invariant basically says this. 1 second. Invariant. It says that all internal nodes precede external nodes. 1 second. Nodes, gosh darn it, of the same weight. What does that mean? Well, it means that, let's say, I don't know, we have an external node of weight 2 and an internal node of weight 2. The external node will be a lower number, which is weird why they use the word precede, but they do. Let me see. So A node P is a leaf. Oh, I'm sorry. Here's what it is. All internal nodes have a... 1 second. Yeah, all internal nodes have a higher weight. And let me see here. I think I might have gotten this mixed up. For weight, all leaves. Yeah, leaves precede. Bah. I'm doing a really bad job of this. But that's okay. All external. Internal. Okay. Let's see if I can get at least the last two right. So page, new page before. 3. We have 2 more things to take into account. And that's that all of the external or internal nodes that share the same weight are in the same block. And each block has a block leader. This looks like this. So if we draw something like this, here are all of our nodes. And we put weights on all these nodes. 1, 1, 1, 1, 2, 2, 4. Here, we can create a whole bunch of different blocks. Here's one block. Here's a second block. And here's the third block. And there we go. We have all our blocks, and the leader of the block will be here, here, and here, being the node with the highest internal numbering scheme. Okay, good. So we have just identified all of this. Now the question is, what do we do? What is the point of dynamic Huffman encoding? Let me get a quick sip of water, and then I will describe that, and we'll keep going from there. Ah, man. I definitely have a headache. And then I got water in my eye. Gosh darn it. Okay, that's okay. We are definitely good to go. I think this is a bit misleading. Members of the block doesn't have to be the same level. You're right, they don't. Which we'll talk about in just a second. At the same time, I think it's a good example, so it easily describes where the blocks are. But that's okay. So let's take a look at an actual... okay. What is dynamic Huffman encoding? Why do we want to do it? Well, dynamic Huffman encoding is different than normal Huffman encoding. How do you even manage that? Oh, getting water in my eye? I think it's because it like splashed back up. It made like a little water jet just right into my eye. Okay, anyway, what are we going to do next? Okay, so let's say we have the following phrase. A, D, D. Those were D's. D, D, B, B, C. Something like that. Okay, what we do is instead of going through the entire string and creating a frequency for how many A, B, D's, and C's we see, we instead go letter by letter. And we create the tree one letter at a time. So we start with nothing, the 0 node. And the first thing we do is if we have a 0 node, we create 2 nodes. A new 0 node to the left and another empty node to the right, which is our very first leaf node. Okay, now what we do is we take this guy right here, we move it to the front of its block, and then we increment its value by 1 and the value of this leaf node by 1. Okay, so we kind of continually do something like this. What I'm going to do is instead of encoding this phrase right here, I'm going to encode a phrase that we use quite a lot, which is hello. So let's start one step at a time. We've got our initial 0 node. We create a 0 node over here, and we create H0. These guys both get incremented by 1. So we have H1 leading to the root node, which is 1. Okay, now we put in an E. Well, that means we go down here, and I'm going to put this in blue, create a new 0 node here, and create a new leaf node for E1. Okay, now what do? Well, we move this guy in front of its block, so that means this guy moves over here. So now we have 2, 1, E1. Oh gosh, I am screwing up with notation. E1, 0, H1. Okay, so now we have our 0 node here. We add in a new 0 node. Again, I'll do this in blue, I think. Okay, so now we have a new 0 node here and a new node for L. So we'll do L1. Okay, so this one's a little bit weird. Let me think. What do we need to do here? Well, this guy right here needs to move to the start of all of the 1 nodes, right? So all of the 1 leaves. So that means it needs to move over here, which means this guy needs to move somewhere. Where is it going to move? Well, it has to move over here, and this guy has to move over here, creating a new tree that looks like this. It's going to be 3, then it's going to be 1, L1, 0, 2, let's see, H1, and E1. Okay, so this is what ended up happening. We implemented a function known as increment and slide. The idea is that we slide our internal node in front of all of the leaf nodes of the weight it's going to be. Then we increment its weight, and we slide all of the other leaf nodes of weight, whatever it was, in this case 1, back 1 element. So because these were implicitly numbered, they basically looked like this: 1, 2, 3, 4, 5, 6, 7. We moved 3 to 5 because that's the leader of that block. 5 then needed to move to 4, and 4 needed to move to 3. And that was how that worked. So now we have to add in another L, okay? So that means we're incrementing this guy right here. Okay? So the first thing we do if we're incrementing a leaf node is we switch it with this guy right here. So let's go ahead and do that. L and H. And then we do the same thing we did before. We move it to the start of all of the internal nodes of equal weight. So then we move this over here, which in turn bumps this guy over here. And we have the following. So if we move this way, we see that we have 4, L at 2. Then we do, what is this, 3? And it should be E1. Then we do, wait a minute, I think, oh, we should totally have 4. This is a 2. Then we do 1, 0, H1. Okay, so let me go ahead and redraw this on the new page. It's going to be 4, L at 2. Then we do 2 over here. This will be E at 1. 1. Then we have 0. And of course, H at 1. Okay. Hey, H26, what's up? We are continuing to work on the dynamic Huffman stuff. I have been gone for like a week, so we're kind of starting from semi-fresh. Okay, so now we have the last character to add in, which is an O. It does the same thing as it did before. Are you sure you need to do the move on the first E? Pretty sure. So I'm following. Are you sure you need to do the move on the first E? Let's see. Let me go back. We added an E in here. Yeah, so you're saying, do we need to move this E back? If you look at figure 7 on page 840, here, let me go ahead and pull it up. So where are we? We are here. So we have HEL, and let me go over here to Vidder algorithm. I think I said what, 840? Oh, different. Darn, different paper. I think I accidentally deleted the paper I needed. Let me go here. 1 second. I think I said 840. I did. 1 second. Still scrolling. Okay. What do we have here? Okay, so we have this algorithm here being done for the phrase ABCD, right? So it should be. Just had a cat rescue lady stop by today. I taught her 2-person kitten nail clipping technique I came up with. It seems like it's probably quite efficient. I thought that clipping cat nails was considered. Are you allowed to do that? I thought, like, I guess you are. I guess declawing a cat is totally something that happens. Okay, let's see what we have. So it looks like it's ABC. What did I have? I had HEL. Let's see. So what did I do? We moved the E to the start. Oh, okay. Wait, what's the difference between the nails and claws then? I know so little about cats. Okay. So let me go back over here. Yeah, I'm taking a look. I'm trying to think here. Okay. Yeah, I know which one you're talking about. I'm trying to think. So what did I do? I said that the E right there, that guy needs to move. Oh, you're talking about the swap between that 0 and the leaf nodes of 1. Okay, so you're saying just the swap between these guys here. It's the leader of its internal block. However, with this algorithm for the increment and slide, we actually move. We have an if statement. Let's see in the Pascal code. 1 second. One second. Let me see if I can find this increment slide. Oh gosh, I really don't like how these papers were outlined. Again, these were the best ones I found. Okay, so here it is. If P is a leaf and B is a block of internal nodes of weight T, or if P is an internal node and B is a block of leaves of weight plus 1. So it's on page 839. Okay, so if P is a leaf and B is a block of internal nodes of weight, right? Or P is an internal node and B is a block of leaves weight plus 1. So with the internal nodes, we actually go in front of all of the leaves of weight plus 1. And that's the idea here. So you do have to switch it because they move, all the internal nodes move in front of all of the external nodes of weight plus 1. So it needs to move in front of all the external nodes of weight 1. And let me see, what did we do? Yeah, so that's an external node of weight 1. So I'm fairly confident in saying that's correct. Okay, so let's see. Clipping a cat's claws just removes the excess so they stop being like razor blades. You don't just clip them all the way and hit the fleshy tissue at the nail. Okay. And I guess if you cut all the way, like you completely remove the cat's claw, then it doesn't grow back. Is that what happens? Not sure. Okay, so we're going to add in the last node here, which is going to be a 0. And then we move in a, 1 second, 0 or an O, sorry, with a weight of 1. This guy needs to move in front of One second. This guy right here, which means this guy needs to move there. This guy needs to move there. So in the end, we have 5, L of 2, 3, 0, I'm sorry, O, 1, 2, wait, shoot, screwing up. This should be a 1, this should be a 1, no 2, and this should be a 0 node, O1. And then we have H1 and E1, which should be quite similar. One second. Before the letter D is processed. Yeah, okay. Which I think should be correct. So we have this here. Okay. And actually, one second. When this guy is updated, it might need to move in front of this guy, but that's okay. For now, we'll kind of leave it here. I think this is right. I might be missing a final step, but it's certainly getting there, and you guys get the idea. The idea is that we dynamically create our tree as we go along, and this is, of course, our encoding scheme. So as we create this this encoding scheme throughout the process, we're going to create a different set of code words to use. No, if you clip too far, make the cat bleed. If you want them gone, you need to have the surgically removed, but I don't suggest this as it affects the cat quite a bit psychologically. Yeah, I mean, I could imagine if I woke up without fingers, that would also be quite traumatic, right? I mean, that's kind of the same thing, because cats use the claws literally to climb up things because they don't have opposable thumbs. I mean, it's basically, I don't know, their equivalent of thumbs, I guess. So, anyway, okay. This is kind of the idea here. We create our tree dynamically, and we need to work on a couple of different things to get this to work in code. As of last week, we started getting there. However, I got sick, and now I don't remember where we left off. So this is going to be rather interesting. I don't know what we actually need to do, but hopefully we will be able to remember together and get stuff done. Of course, if you guys have suggestions, let me know. I will totally take suggestions as we go through. And what else do I need to say? I will take a look at those links that I have saved for the dynamic Huffman stuff tonight. But I think I already saw the links before. I'm not sure. So we'll see how they go. Okay. But yeah, for clipping cat, they generally naturally know their claws are powerful, and having them clip limits this power. Yeah, I mean, it's like, again, waking up without thumbs or fingers or something. It's pretty traumatic, I would imagine. Okay, so let's go ahead and CD into the appropriate directory. CD projects. One second, projects, Simuleos and Huffman. Do the same thing over here. CD projects, Simuleos and Huffman. Okay. So, what do we need to do? So I use jujitsu principles for blocking the joints so the cat cannot attack me while I do it. Really? What do? Do you just like hit the joints really hard and force them not? Huh. Okay, I'm gonna get another sip of water, and then we'll be good to go from there. Again, if you have any questions, let me know. I'll totally address the questions as soon as I see them in chat. And yeah, we'll get started after that. I don't really know much about jiu-jitsu. I'm not gonna lie. Okay, also, I will be right back. I apologize for leaving stream, but I really, I'll be back in a second. Okay. Wait a minute. Krabs, you talk to your cats and they understand what you're saying? Because, like, that is a multi-million dollar business right there. Like, you could make money just talking to people's cats and telling them what not to do. Okay. 1 second. Okay. Sorry about leaving stream so much. I'm kind of still not feeling so well. So, I had to go like blow my nose and stuff like that. Anyway, foster cats, kittens, they're not always well behaved. Some very skittish. So with the kitten method, I always hold my hands together so my thumbs are away from each other. Okay. So let's do LS here. And, dag nabbit, I'll be back in again. Sorry about that. Dang. Okay, now I'm good. Okay, so this blocks their front paws from moving, and my index fingers goes on their belly, and rest my finger. Okay, 1 second. Baby cats. Okay, so let's go ahead and go into the Vitter algorithm. Actually, what is animation nothing.gif? I don't know. So let's do Mirage animation nothing. What is this? Okay, this is just our basic animation. Nima. Oh, that's the name of my machine. I don't know why I called this animation nothing. I need to get a better naming scheme here. Nima is the name of my machine. I used to do a lot of writing. And I created a whole bunch of characters while writing that I reused a whole bunch. So the character Leos was always the main character, Leos. That's why I kind of stuck with Leos as, you know, my main name on the internet. So Leos OS or Simuleos or something like that. Always a play on the name Leos. Another name I use a lot, like on Reddit, is Kedem, Qedem. The name Nima actually was one of my my favorite characters that I wrote about. I don't actually remember what Nima means. What does Nima mean? Thought. What is thought about? Yeah, I don't actually remember what it means. It probably came from Greek or something like that. Nah, it was just a character I used to write about. She was this little girl that had like a fantastic imagination and could always create things, and I don't know. She was just a neat character to write. I enjoyed writing her character a lot. Okay, so let's go ahead and go into the Vitter algorithm and let's see how much damage we can do. Okay, vitter.cpp. Where were we? Okay, I remember now. We were trying to see if we could figure out how to use that find leader command. So what we needed to use the find leader command is we needed a vector of nodes, internal and external. And I believe right when we ended the last stream, we had our list of nodes. Are the stories somewhere online and readable? Not really, no. So again, before I became a scientist, I wanted to become an author. I really, really wanted to become an author. I used to write like hundreds of pages every month. Like I remember at some point I had a document that was 1,200 pages long, just completely filled with one story. And I don't know. I never really open these up because it always ended up being that after writing a chapter, my writing style changed so much by the time I started and ended the chapter that it wouldn't be consistent. And so I just never really felt comfortable showing people my writing because of that. And so to this day, they are kind of stowed on a hard drive somewhere that I don't actually remember where it is. So you'd be like Asimov and be a science author writing both scientific papers and fiction. That would be cool, except for the fact that if people start realizing that I write fiction, they might, I don't know, they might not like that very much. One thing I would point out, though, is that I do have a side account that I do a lot of writing prompts on Reddit. Every once in a while, they turn they turn out okay. Yeah, actually, I do enjoy writing. Every now and again, like, if I can't think of anything to do, like, for example, this past week when I was really, really sick, well, it wasn't really, really sick, but sick enough that I couldn't really do anything, I ended up doing a lot of writing that time. I also played a little bit of Guild Wars 2, I'm not going to lie, but I did a lot of writing, and it was fun. It'd been a very long time since I just kind of sat down and did it. So, I gotta admit, it's a pretty good, not time dump, but pretty good therapeutic thing for me. In fact, if this stream wasn't a programming stream, if it was like a typical gaming stream, I would probably devote a day, a week, just to doing writing, because it's something I do enjoy a good bit. But that's kind of beside the point. Okay, what we need to do is test out this find leader function, obviously because we need the find leader function for the dynamic Huffman encoding algorithm. So let's go back into our Huffman.cpp function, ls here, and let's see what we got. Did I tell you about the hardware project that I've got planned? No, you did not. I was very lucky with my cats, only targeting vets. Vet always needs leather gloves. Okay, so what do we have now? Let's go into Huffman.cpp and let's see what we got. So I think, yeah, the main file isn't actually in Huffman.cpp. The main file is in Huffman visualization. Visualization. Oh, come on. I can do an underscore. Visualization. .cpp. Okay, now let's go down to main. Let's go down to main. Okay. What do I have down here? We have node keyword generated nodes, draw encoding. Here's what we want to do. We want to basically do this entire function that we were doing before, the 2-pass Huffman encoding, everything like that, except in this case, we basically want to skip. Yeah, that was my bad. I actually opened up the binary file instead of opening up the CPP file. Oh well, that's okay. Okay. So what we want to do is a Huffman visualization code, except this time we don't want to do the drawing. So actually, what I'm going to do here is wquit vi huffman.cpp, and we're actually just going to leave main in for now, dd, and down here. Okay. So we have all the character keys read in unordered map phase. Okay. So let's see what we got here. Nisimico, do I consider myself a developer, or are you talking about Edge? Sorry about that. Edge 226. I do not consider myself a developer. Actually, I don't develop software. I do a lot of programming, but I don't develop software. The closest thing I do is the daemon simulation code, dynamic exploration of microparticle clouds optimized numerically, which is for dusty particles in a magnetized dusty plasma. And I do the gross PDSky equation solved on GPUs, which is the GPUE code. These are both research codes that people use in their professional careers. So you could argue in some cases, you could argue that this is scientific software. At the same time, I wouldn't consider myself a developer, because it's a little bit weird. One second. Here's my channel. Here's all my notes about how I was sick the past week. Let's scroll down. And my GitHub account is right here. Okay, the codes I was talking about were Laos. This one right here, my daemon simulation code. And then another code I've been working on quite a lot recently, which is GPUE. Here. So these are the only two softwares that I would consider, two pieces of software that I would really consider. Yeah, see, this is why. Actual software that people use. And even then, it's not real software. You know, it's scientific software. So it's not the same. So, I know some of these words. Oh, Guild Wars 2. That's fair. I play Guild Wars 2. What can I say? They just released Season 3 of The Living World, and it's actually really good. Did it? Let me see something. Oh gosh, I'm now terrified of things that are popping up. Oh, it did not. What? Wait, how did it pop up? Oh, it did. I was certainly not searching Guild Wars 2 on GPUE. I'm going to do 2 times Raspberry Pi mobile computing platform. It's going to have a day and night camera with light sensors, and I'm going to program to calculate the camera should take a picture. Wait. What are you taking a picture of? Like, how does it know to take a picture? If, like, are you taking a picture of people, or are you taking a picture of the sky? It's going to basically do everything a phone can do, except the whole phone stuff. So... the only phone I have is this one. So I guess it's gonna play Snake? I don't know. Actually, this one can't even play Snake. Oh, actually, nope. Here's my Japanese phone. It's pretty good. Okay. I've been looking for that for months. It was on my desk. Okay, so it's going to have an LCD screen. But you said it's going to take pictures. What camera should take... oh, what camera should take the picture? Oh, I misread it. Okay, I thought you said when it was going to take... yeah. Yeah. Okay, so let's see. What we're going to do. We need to find our vector of internal and external nodes. I believe, unless I'm completely out of it, that we have our vectors being written now. So what I want to do is, after our decoding, and we write everything out, I want to then do something here. So we have our Huffman tree, final tree being created. Let's do the following. For int I equals 0, I less than, let's do final tree dot, what did we call it? vi huffman.h. Scroll down a little bit to our Huffman tree, and we have internal and external. Huffman tree.internal.size. Then we do ++i. I believe the internal and oh, they're going to be different sizes, definitely. So we're going to go down here. We're going to do std cout. And I guess what I want to see out is internal.wait. So final tree. And let's go through a different looping scheme real quick. So we're going to do auto. 1 second. Let's do auto. And I guess we'll say element. I can't think of a good name for this. So let's see, internal node. No, we're already using node. Element, let's do it. Within final tree. Dot internal. And then we should std cout element. Pointing to wait. And that should be okay. New line. Let's write this, and let's see what happens if we just go ahead and compile this. So if we do g++ huffman.cpp, let's see what we got. Good. 1 second. G++. That's what I thought. Okay, so let's go into vi huffman visualization.cpp, and let's go down to main. Okay, so we have basically the same thing that we want outside of this. So final tree, wait, node queue, decode. Let's String phrase. Good. Okay, so let's go ahead and remove some of the unnecessary lines here. Okay, let's see what happens if we write this. String phrase, Huffman tree 2-pass Huffman. This should be perfectly fine. Run quit. Now let's do the last G++ command. Okay, this one seems to compile. Now let's see what happens if we go down here. G++ also seems to compile. Good, so we are outputting node weights. Now we're going to go down here, and we're going to say for auto element in final tree dot-external. Then we say stdcout element pointing to weight. Actually, let's do key and line. Okay, so now let's write this, and let's do G++ Huffman a dot out. Okay, good. Everything seems fine. So this means that we are at least creating our vectors of internal and external nodes just fine. Now let's move on to the next step, which is finding the leader of each individual block. So let's go ahead and write and quit. From now on, we'll just be using the make command. So let me go into the make command. Let's see what we got. I've already commented out everything but the vidder function here. So let's go ahead and write and quit. vi vidder.cpp. Good. Again, guys, if you have any questions, comments, concerns, let me know. Of course, everyone kitten pictures, that's I guess how it goes. Okay, so now we have to find a way to make sure that we are actually writing out the appropriate leader to every block. And this is kind of a bit of the hard thing. We have to think about how we're going to appropriately order all of these characters, right? So like we have before, we have the find leader requires a very specific order. And we say word 1, largest, and then a couple of different word 1s, word 2 largest, and then a couple of different word 2s, word 3 largest. So basically, weight is actually what the W's I think stand for, but we want to make sure that when we put the weights into our vectors of internal and external nodes, that we do so with the largest weight at the very front of the blocks, if that makes sense. So they're all going to be in the same list of internal and external nodes, but we need to make sure that in this list we have everything kind of ordered appropriately so we can find the leader. At this point, I don't believe the vidder algorithm is on GitHub that we have so far. So let me go ahead and write and quit, and let me check real quick. So git status dot, and let's see, we do not have modified. No, the vidder.cpp file is not yet on GitHub. Why wasn't it on GitHub? I don't remember. So let me go here, ls, and let's go into the vidder algorithm again. Oh, .cpp. So let's go down to main, which I should have. Yep, sure do. And I have all these lines commented out. I don't think they're necessary right now because I think the find leader works as it is. What are we doing in main? We're creating our phrase. Jack and Jill went up the hill to fetch a pail of water. Jack fell down, broke his crown, and Jill came tumbling after. Same thing that we have been using for a while now. And we are creating a Huffman tree by doing the 2-pass Huffman algorithm. We create an unordered map, block positions. Okay. And then we basically go through all internal nodes. Good. External node, leader weight is good. So then we just go and we call all the leader weights. Now we have to actually think about how we're going to do this with the vidder algorithm. So we need at least a couple of different functions. One would be the vidder function. The other would be the slide and increment function. So we have our phrase. I guess we just go through and we start encoding the phrase. And we take it one step at a time. So again, a lot of the pseudocode here can be found between the two papers that I linked before. If you want me to, I can link the two papers again. In fact, maybe it's best for me to go ahead and do so. So the first paper to read is this one right here. because this kind of gives you a good intuitive feel for what we're working with. And the other one is this one right here, which kind of gives some pseudocode in Pascal. Now, that said, I have trouble reading Pascal, so if you're like me, maybe read that one with a grain of salt, but it's still there in case you need to look at it. I got some good information from that one. Okay, so void vitter, string phrase. We have the phrase, we're going in. Let's just go step by step and encode every individual letter. So, how are we going to do this? Well, we already have the pseudocode available to us at, 1 second, where is it? Here it is, page 839 of the document. So let's go here, 839, that's 38. I was already there. Here it is. Okay, so first thing we need to do is kind of implement this guy right here. I have it on my own desk. So I will be kind of looking at my own copy, but again, it is available online. I just gave you guys a link, so feel free to take a look at that as we go through. So first thing we do is we check to see, is this leaf already in the tree? So the first check, 1 second, is that. So first, if the new leaf is in the tree. Okay, so how are we going to do that? We can do that in a number of ways. Let me think. We have a list of all the internal nodes already, right? So there's probably a way to go through and check to see if external nodes is what we need, but we have a list of all the we have a list of all the external nodes. So we should just be able to go through all the external nodes and check to see their characters, right? That's one way to do it. Yeah. So let's go ahead and create a new function. And this function will be, I guess, I don't know what we should call the function, but that's okay. We'll come up with a name in a second. Those are no longer necessary. So we're going to want Boolean, and what do we want? We want to say, is this external node, the one that we're reading in, the letter like J or A or C or K, is this letter already in the tree? So I guess we'll say in tree. Okay, and we want a list of nodes, so vector of node star, I believe, internal. And then we also need, I guess it's a character, but we'll do std string. I know it should just be character. What do we put down? vi huffman.h. We put down character, so we need character. Character key, character string, character new key. Okay. Good. So now we just have to write this function. Go down to the bottom and let's get this written. I'm gonna write this in. See, and this is why I have been using a different mouse. Okay.